Hello, welcome. Let me test if the audio is good here. I actually forgot to close the door. Oh, thanks, Michael. Yeah, so I don't annoy too much my colleagues around here. So for anybody who's currently online, if you can please confirm the audio is good. Let me ask a couple of colleagues here. I know it shall be okay, but doesn't hurt asking. So let me check with my colleagues here. Oh, thanks, one. So you already did. So let me. Oh, sorry, I was showing this window, but nothing really important showed up. Let me make sure I don't have anything popping up. Okay, all good. Okay, so let's go straight to the point here. Let me change. So we're gonna go back to our Quantum 3 starting project that we started developing last week to show as many features of Quantum as possible. So let me stop this thing from prevent this thing from creating notifications. Okay, good, done. Yeah, I put it in German this time, Juan. I was wondering. I actually did it last week, and I was wondering when somebody would notice it. So, um, okay, let me check. Sorry, I just have a priority question here coming. So. Okay, so this is our project. Let me just press play here and we see what's going on. I did a couple of offline modifications, mostly cosmetic stuff, but let me list them for you here. So first, we have a checkered pattern on the floor, so this lets us perceive the movement a bit better. I added the character rotation, so now actually the character looks towards where he's walking to. Another thing, when you jump, it doesn't think it's walking anymore. It's not really. I don't have a jump animation, but I can show the change on the animation script. It's really minimum. And I made our camera a little bit more fluid. So first, it doesn't move when you jump, so you can really perceive the jump movement. So the camera does not go up and down. And it's a bit smoothed when you move around. So it's it feels a bit more fluid, but it's really cosmetic stuff. So we can take a look at what I did here. So the animation view, essentially, I check if we're also grounded to apply the speed stuff. So we'll actually only make the character walk if you're grounded. It will not activate the walking animation unless you're grounded. And yeah, that was basically it for the animation. And for the camera follow, I added a bit of lerping and offset positions. I even experimented with an offset position on the for where the camera looks at, but I did not really like the results of that. And because it was not really important, I'm not using that part. So I'm not using the look offset. It did not really work as I liked it to. So this is kind of making the camera look a bit ahead of the character, and if I move down, it would look. But it's kind of annoying. See, I did not. And if you move sideways, it does this. So, well, I could have made it more elaborate to feel better, or perhaps I should make my movement be relative to the camera and do a proper 3D platformer camera and input system, which is a bit like how Mario Super Mario 64 use camera and input. So well, I could do that, but that's honestly not the point. So let's stop short and that's it. So these are the modifications I did, just that. So the rotation stuff is super simple. So on the movement system, I just so we have the previous stuff, and what I do is I check the velocity of the character. If it's big enough, I make the character look into the direction of the velocity using some of the quaternion helper methods we have. So it's super simple stuff. Nothing. Let me increase the font size a bit here. So nothing really complicated, not specific to quantum, more like gameplay stuff. So I'm not gonna focus on that. I just wanted to have something that feels better to demonstrate. Let's go now to the actual points. So point number one, I'd like to start by I think I can have some internal stuff I was working on here, but let me get my the file. Yeah, so so I have a list of things here that I was planning for today. So I think I have a few more things. Let me grab here from the yeah, I have also time slicing that I want to demonstrate. So I also want to demonstrate this, hopefully, and event polling performance. Yeah, that's it. So these are the topics we're going to talk about today. So, but first, I will start again with the asset stuff, because we had an issue on the previous stream when I was talking about assets, and there was a little bug on the asset creation menu, but there was also a misunderstanding from my end, and I'm gonna explain that again. So we have here our character prefab, and I explained that we can have this concept of immutable assets, and immutable assets are, in the end, they become Unity scriptable objects. They have the same purpose, and actually in Quantum 3, they are literally scriptable objects. In Quantum 2, we load them inside scriptable object wrappers, but in Quantum 3, they're literally scriptable objects. And you can use inheritance in that and have this, there is a lot of stuff on the documentation too, and on the samples showing what you can do with that, but we had a problem with it. So, but let me show, I'll close everything here and we'll open from the beginning. So to use an asset in Quantum 3 now, essentially you can have these classes to represent immutable data. So the way to reference them into a predict rollback data struct, a struct or a component is basically now this asset ref with the generic type of the class, asset class you are trying to say. So in this case, our character points to an immutable spec reference object. And you don't have anymore to do anything like assets and then declare a type. So nothing like that, because we don't code generate anything for these anymore. They're generic here. They're generic on the C# file. There is no necessity to do any of that. So this is also a perk of being able to upgrade to a greater Unity version. So originally in Quantum, we had to support a very old Unity version. So you just do this. So, okay, here's my reference to a spec. And let me show, so our character spec in this case, this is a fully fledged example that has even an abstract version of the character spec. So we're referencing saying, hey, the character spec is this reference here, but this is an abstract type. So because we're going to demonstrate polymorphic methods here, and any concrete class will come with the base power that is declared here. But let me show you, I added two concrete types. So special character spec inherits that and adds a special power thing. And there is also a variation character spec that I didn't add anything here. I could have added different data. I could have just made the method polymorphic, the update method, whatever type of method you add here. So nothing changed yet. But these are concrete classes, so they're not abstract. So we can have instances of these. So then on our so we have a system to go with it to demonstrate how this works. So um, essentially on when the character stats component is added, we initialize some data in the component based on the specs. Let's say you can also reinitialize this on when the character is respawned or something like that. And the only thing we did here is that, okay, we're going to find the asset based on the spec, and this is going to return the generic type, which is the superclass. In this case, it's going to be character spec. We don't know if this is which of the concrete classes this is, because the declaration just says it's a character asset, which is the abstract superclass. But doesn't matter, they all have base power. We can always do this. Or we can even create a method passing as a parameter the pointer to the component, so it initializes the component based on a polymorphic different initialization. But we demonstrate polymorphism here with the update method. So we on the update of the entities, we grab again the reference to the spec, and we call update stats. And this method here is the abstract version of it here, but you don't know if it's this implementation or this implementation that is being used. It depends on the concrete type that's being linked to our entity. So let's show how. So this is how the code works. Data-driven polymorphism, just like demonstrated on the documentation example. And let me just show how the assets can be created here. I actually created one here. I could delete it, but we modified a bit this because that's where the bug was. So now there is a new window for creating assets. Before we had all the asset types kind of like at the end here for the pre-built assets, because a lot of the stuff Quantum, a lot of the configuration things Quantum has, like simulation config, character controller config, nav mesh agents, physics material, a lot of these things are actually Quantum assets as well. So the filter, the system list asset, that's also a Quantum asset. So we had the pre-built ones pre-listed, and we thought that this menu was getting too crowded. So we added Piotr added for us a custom window here that shows all the asset types, and it includes now correctly the inheritance-based stuff. So we cannot actually spawn the abstract one because it's abstract, but we can actually create for the concrete types. If I click here, it's actually going to create it. And you can also search. So spec, and then it shows only the concrete ones that you can do. So it's very convenient. And I'm going to create a variation character spec here. So variation spec. So then this is a variation one. It doesn't add any data. It's just the original data. The special spec one has both the base power and the special power. And they are assets in Quantum. When we're creating our character here on our prototype, we can link the specs. So this link here is type safe. You can only drag and drop here character specs, but of any of the subtypes of the abstract class. So we can either drag and drop this guy or this guy. Will accept. It will only accept concrete instances on the scriptable objects that are of the special type, the specific types. So I think in this case here, where is the sometimes the Unity DB. Where do I generate the Unity DB? No. Sometimes I don't need to do map data. No, it's not that. So there is a way to generate the DB. Let me try to open the DB. When we have an issue with the oh, it's not. Oh, it's okay now. Yeah. Sometimes you just need to regenerate the asset DB, but it fixes itself as well by saving. So yeah, you can only drag and drop these. These are the concrete types. That's all. So if we press play here, I think we're using the special one. Doesn't matter. So if we add the logs there, the code in that system is gonna log that we initialized based on the concrete type. We could, for example, log here what the type is. So let's say log.info. just to finish this once and for all, we can do spec.type dot name or full name. Name is okay. So this is going to just print the type that was loaded here, the concrete type. So if you look into the console, press play, because the system that does that is running. So we see that it's a special character, spec here on the log. So that's the spec that this character is using. If I modify this to be the variation spec as it is already here, I can save the prefab now. And if I press, it's clear here, press play again, and we see it again. And now it is the variation character spec. And all the things are being done polymorphically now. So that's it. I wanted to get this sorted. We had an issue on the previous stream on this topic, but it's all fixed. So whoever get the nightly, this is all working correctly now. Then we can move on to the next topic, which is events versus polling. So this is an interesting question a lot of people ask, which is, when doing these visual things, like for example, the animation view, I'll use as an example an animation. So an interesting example would be jump. So should we apply should we constantly read poll data from the simulation and update our view like we're doing here? Or should we use events? Events allow us to define little pieces of data that you can trigger from the simulation, and you can add callbacks on the Unity side to receive them. And it's very convenient and adds and gives us a lot of flexibility into many things, but there is always a trade-off. So to start with events, let's create a basic event here. So let's say, so we have on our stats, we have a power thing. So let's say power depleted or something like this. So let's say we do power depleted, and we're gonna do entity, I think entity ref, entity, and maybe this is enough. So let's say we get something like this, and let's say power restored instead of power depleted. So let's generate this event here. So that's all we need. So it's an event, and it informs what's the entity to do this. So first, how can we trigger this, and how can we subscribe on Unity to receive this? So to trigger it, let's use our character system thing, and when we initialize the whole thing, yeah. Oh, maybe I should, although I would have, that's a good point. So I think I should new power, something like this. So I want to use this because I want to use this to exemplify a difference between polling the data and using an event for this. So this is a very good thing to demonstrate it. So let's so when this is code generated, we can here go on the system, and for example, I can go frame dot events dot, and then you have all the events that were code generated here as methods, and you would have as parameters the things you defined as components on as fields on the event. So in this case, it's the entity, and the power that we got as the new power will be whatever is the power on the component now. So that's all we have to do on the event. And here's a cool thing about it. So it doesn't matter if this is being resimulated, called multiple times. If you call this on a specific frame with specific values, it will be triggered on Unity only the first time this happens. And there is a way to defer this to happen only on verified frames. We're going to talk about it soon. So this is already being triggered at the beginning. What we need to do now is, okay, how do we on Unity can subscribe to that event? So let me see if that works, or if I should perhaps add it somewhere else. I need to check because I think my bind behavior here is verified, so it might not happen right away. Oh, it's non-verified, so it shall work. So I'm reluctant here if I should demonstrate on an existing script or do another one. I'm gonna do on this existing script. So I'll grab the manual here because we do have an entry about events and callbacks that is very handy, and it explains all of the topics about this. So I will not cover everything during the stream, but I'll add a few examples. But here's how we can subscribe to a specific event. I'm just gonna copy this here and add to our script, but I'm gonna use a specific method, and the name is gonna be event power restored. Here it is. So this is the name of our event. I could just have this here, or I could create a method to handle it. So let's add here a void handle power event, and then the name is, we need this guy, and we can just here call handle power event E. I'll get to Jaden question in a minute, okay? So let me just finish this here. So then we can do E dot, so we have, I'll check if E dot entity is the same as my entity ref, because if it's not, I will not do anything. If it is, I will use Unity debug.log new power plus E dot F dot new power. So we can just log this. I need to check if this is gonna work, because I might be dispatching the events after the entities are spawned or before it. In that case, I will use a different script for that, but let's see. No, it's actually working. It's handling them after the entity is spawned, so that's good. So here it is. We got our event showing it. So so now let's get to the difference. Should we use this, like react to events, or should we use polling from an update method? So both cases are kind of zero allocation, right? So when you're reading our ECS data, this is all non-allocating, so it's all clean. But events are also non-allocating, because although they are classes, they have we have an automatic pool for all these generated event types. So as soon as an event is dispatched and consumed from your method, it's returned to the pool, and it does not cause GC spikes or things like that. So as long as you use them reasonably, you do not dispatch like thousands and thousands and thousands of events every frame, it shall be just fine. So the question is, should we use events or should we use polling? It depends. So when you fire an event, you may not have necessarily the same frame available anymore, because let's say if you are predicting 10 frames ahead and the event happened on the 5th of these frames, this frame is between the verified frame you have and the latest predicted you have. That frame data does not exist anymore. So you either have to, so it maybe this guy has been fired from an entity that doesn't even exist anymore on the predicted frame, or maybe, and it may not even have ever existed on the verified frame as well. You may have been creating like very transient entities. So events are good when you can contain the data you need into themselves. The other thing with events is that they are not interpolated. So if you fire an event on the predicted frame, it's going to immediately be called. And sometimes you want to see things in between two frames. So the reason why the views in Quantum are so smooth is because it doesn't matter the update rate of the quantum simulation. So I can, for example, change here so let me see where my resources are. I think I'm using session config. I think I'm using this one here. So if I'm changing the simulation rate to 20, so quantum is running at 20 frames per second, but no, I mean, if you see the visuals, it's actually still running at, yeah, you can clearly see now that the frame number is growing up slower because it's running at 20. So, but of course, the velocity of the character is the same, but not only that, the rendering is definitely 60 hertz still. And that's, maybe it's even more. Yeah, it's actually rendering at 900 frames per second or something like that. In reality, 60 because that's the speed at which my monitor is displaying it, and it's the speed at which I am streaming at 60 hertz. But the point is that we always interpolate between the two last predicted frames. So normally you want to use polling when you have data that you need to be very smooth and data that you have to read as the latest values anyway, and you use events for stuff that you need to be fired immediately. So sometimes it's good to use events, for example, to track some audio effects or some VFXs that you want to be triggered very, very immediately. And in this case, you're going to use regular frame events for that. So where is my doc here? So you're going to use normal events for that. And there is another case, which is when you want to have something that it's guaranteed to have happened, that you want to have the callback called only when the whole thing is confirmed on a verified frame. So you use what we call a synced event for that. So here's the keyword synced that explains. So when you have a synced event, it is deferred to be dispatched only when the frame is actually verified. There are a few other things explained here, like you can, if you add a player ref to an event, you can split that at the dispatcher level to say, hey, only dispatch this to my local Unity if it's a local player, only dispatch if it's a remote player. So you can have these kind of things that they are cleverly filtered by the dispatcher in an automatic way. So it's worth reading this entry here. It's very useful for understanding what you can use for events. But the point between events and polling is you want to use events for these things that you want to be immediately drawn on screen, or for stuff that you want to be confirmed that you don't want to have to be reading all the time. But one big question about events is what happens when you join late into a game, if your game is running and somebody else joins. So because you're not resimulating from the beginning, so this late joiner is going to receive a snapshot, he's not gonna receive previous events. So you should not rely on events to do your whole UI all the time. A good approach is to make sure that you can always initialize your UI from an existing frame by polling everything you need at the first spawn. So for example, the on initialize, actually the on, we're using that on the camera thing, I think. Is it on the camera or animation view? Let me check which view does that. Yeah, the on activate. So you can, for example, from on activate, initialize the UI that's related to the character or something like that, and then rely on events going forward. But never use only events. Especially if you need to support late joins, you need to be able to initialize your UI from the received snapshot, and then to keep it updated, you can rely on events if you want to. So that's the base thing about events versus polling. So I hope this is useful. Again, you guys can ask questions. Let me take a look at the question we have here from Jaden. So does quantum work with Unity ECS in any way or any Photon service? So Jaden, Unity ECS, no. So quantum is a game engine, and we have our own ECS that is mature, production ready, that has been used in hundreds of games already. So we do not use Unity ECS. One of the main reasons for this is that Quantum can run outside Unity also. So you can run Quantum from within Unity. You can run Quantum as a .NET decoupled application to validate replays. You can even run a copy of the simulation on our servers or as a spectator on your own server to store results. So we cannot rely on Unity ECS for that because it would be proprietary to run from a Unity build, and you can do that for you. It would be okay for you to run the game, but it would block you from being able to run simulation outside of in other environments, unless you would have licenses from Unity, and the performance would be dependent on having a Unity build and so on. So we definitely wanted to be independent of that for the simulation, although we are fully coupled and dependent on Unity for the game view and everything. We're not saying that you should build a game without Unity with this. It is totally focused on doing a game with Unity, but you have the ability to run the simulation outside of Unity, and we cannot use Unity ECS for that. So with that said, we do use jobs we trigger when running multi-threaded. In our task system, we actually hook the whole thing with Unity jobs. I'm going to demonstrate this at the end of today's stream. It's the last topic we're going to talk about. And we have a few customers who have been experimenting in replacing the view part of Quantum with Unity ECS. So you can render directly with Unity ECS or Unity ECS animation. And as Unity matures, this whole tool chain for using ECS for rendering, it's certainly something we want to look into that will let you still implement let's say, the simulation with our ECS stuff, as always, with all the advantages of being able to run the simulation outside of Unity, but perhaps using Unity ECS as a lighter weight view as soon as it gets mature. So we have customers doing that, a couple of customers experimenting with that. I haven't seen any major title from our customers go in that direction yet, but I'm pretty sure it's going to happen. And we're probably going to start investigating that as a kind of official support at some point, but we can't guarantee yet. We're waiting for it to become more mature and more widespread in use, but only in that restricted capacity. I mean, there is not really a big reason for you to jump into Unity's ECS. We have a lot of new stuff coming. We have a mature system. We're going to keep improving it on future versions. We have a fully deterministic ECS system that's guaranteed to be cross-platform deterministic with predict rollback and everything. So we can't depend on something that was not designed for this, and especially that cannot run outside of the engine. So we must be able to run outside of the engine, because that's one of the features our customers really like. So no, we don't use. We may use in the future for view. I hope this answers your question. So let's go to the next topic now. So I'd like to comment a bit on physics settings, components, and callbacks. Okay. So I've been using. We haven't been using a lot of physics. We're using a character controller, but we demonstrated at the very beginning. We actually added a quantum 3D, so we could have a capsule entity. We can have a box entity. So let me add a box entity. Where is that guy? So at the scene somewhere. Here it is. So perhaps I should sky to the left a little bit. Let me rotate it a bit here. Rotate here, something like this. So let's see how that goes. If I press play. Oh, what happened to the? Oh, okay. So that box entity is just a collider. It does not have a physics body. So if we take a look at the entity prototype here, it does have a collider with a box, so that's what we're seeing here. Here's the gizmos for it, but it is not a physics body. Let's make that also a physics body. That means it will have a mass, an inertia tensor, and that kind of thing. So if we press play now, that box is gonna fall. Yeah, and we can actually jump over it and do that. Yeah, cool. I think we can push it because we do have a collider. So yeah. So we have that now, and okay, cool. So how can you control physics in any way? So let me give an overview here. So first, on the previous stream, I gave an overview about the quantum configuration files, and one of the files is the simulation config, which is a quantum asset, by the way, that we just talked about. So, and in simulation config, which you can use multiple versions of this asset, you can have different games with different configurations and so on. But one of the things you can change the settings for is physics. And you have a lot of control here about how our solver works. We actually have 2 different solvers that we developed over time. You can set the default gravity. We're moving towards using a native version of the physics library. This is it's an optional thing on Quantum 3.0. This is coming with it's already built for Windows and Android. So a lot of the physics tasks are running in C++ implementation, but we're moving everything to C++. We expect to have everything moved to C++ when we get to Quantum 3.1. But we're already using it experimentally, and it's all cross-platform still. So, but you can set a lot of stuff about solvers. You can, for example, when you don't need to use joints, you don't plan to use joints on your game or something like that. If you disable this, it actually uses less multi-threaded tasks in our task system because we do not even schedule the tasks that run the joint solver and that kind of thing. So you have control of that thing. And because, for example, Quantum is stateless predict rollback physics engine, at least up to 3.0. In 3.1 we plan to change a little bit that. It has a lot more challenges to stacking compared to a forward-only physics engine, for example. So although it can do very interesting stacking already, especially if you play around with some of these things, we have that in the documents and all. But one of the things that if you set a minimum value of push on linear velocity, so a body would only start to be moved if the push to it is big, and it's just big enough. If you put a value, I think something like 0.01 or something, it's already enough. This helps a lot to let the object go to sleep. So playing around with the minimal linear and angular integration helps a lot to put objects to let objects rest and go to sleep, and that helps a lot with stacking. So combining this with allowing sleeping can have so sleeping helps a lot with the performance of physics when you have multiple objects around that can rest, but it also helps with getting stable stacking. But so combining these 2 things is possible. It's your choice. And then, for example, by default we do not use continuous collision detection, but it is something you can enable. And then you can define, okay, we're going to start to actually do speculative collision detections when you get to a minimum velocity of these meters per second, and same for the angular velocity. So you can define all this here. And that's when we start to kick in with continuous collision detection, because and a few other things, you set the default parameters. So this is it for configuration. I mean, you have a great deal of agency into playing around the settings. And when you look, for example, at the physics components, oh, I forgot. There's one other topic that's commonly asked, which is, so what about layers? So normally you would import the layer matrix from Unity, or you can manually edit which layers collide with what. So we use the Unity layers naming. So when you define custom Unity layers, we allow you to control the collisions, the collision detection combination, same way as you do with Unity implementation of PhysX. Oh, damn it! I always think someone. Yeah, okay, so let me show layers again. So thanks. So here it is. So yeah, you can manually define this, or you can just import from the Unity layers as they are and manually do it from here. So it is up to you how to do it. It's a commonly asked stuff. It's how to handle layers. But then you have here at the physics collider itself, you define, okay, you can either set an explicit layer you want to set this collider for, or you can just import it from the game object when you're baking, kind of what you're doing here. It's up to you. And of course, you can flip these layers in runtime at any moment. You can always do that. But another interesting thing you control per entity here is whereas this entity is going to receive callbacks or not. Because by default, entities are not set to receive any physics callback. So if you have two entities touching each other, what defines if they're going to receive, if you're going to have a physics callback that you implement being called or not? It depends on the settings of both of them, right? So I'll give an example here. So I'll show this. So I'll demonstrate with one example, and we will I'll demonstrate with one of the collision callback examples, and then the other examples are straightforward. You would understand them. So we have separate events for collision state that we just call collision. But most importantly, we have a difference between when an entity is colliding with another entity that's on dynamic collision, or when an entity is colliding with a static obstacle, like this floor is a static collider, so it's on static collision. And of course, you have enter-exit callbacks as well, and the same will happen with triggers. Also duplicate between dynamic, and dynamic static. So I'll focus on doing the dynamic collision enter to show how these callbacks work. So I will not set callbacks on this box, and I will not set the callbacks on the character at all, but I will implement the method on a system, so then we can test if it works or not. So let's make our movement system. Perhaps I'm going to demonstrate something else. I'm going to create a specific system just for that. So I'll create quantum system. It will not be a filter system. This is going to be my collision system. I'm going to use the system template. It's the basic system template. This is a system main thread. I'm actually modifying that to be a system signals only. This is pretty cool. It's a system that does not have any update method. It's just a system that you can have that will react to signals if you implement signals in them. And collision callbacks are signals. I signal on. So we're interested in the on collision enter 3D, which is the one I want to demonstrate with. The one I want to demonstrate this whole thing with. So implementing the signal allows us to receive, so info dot. We have entity and we have other. So this is a dynamic collision. So, actually this is the same, whereas if it's a static or not. So if this is a dynamic collision, info is going to have, it doesn't say it's dynamic. So dot is static equals false. So this is a dynamic. Collision is one that is not static, but of course I can also check the second entity not being default. So the same thing would be if I also test info dot other different than default. So that's the same. Means that we're colliding with another entity. So it's a dynamic collision, and we're it's the enter. It's going to be called first time the collision happens, not second time. I think in our examples we might hit this multiple times because we're going to be pushing the box in the example, but let's see. What I'm going to do here is I'm going to do log dot info. I'm going to actually show info dot entity, first entity plus collided with, then info dot other. So this shows which entity collided with what. And let's see what happens if I press play here. Oh, our system is not running, so we have to add the system to our list. So our systems, I cleaned up this a bit, so I need an 8th system, and this is going to be the my collision system, the one that we just created. So this is part of the systems that we have. It doesn't run, it doesn't have an update, but we'll run it here, and well, can already see nothing. So I'm gonna touch on this guy, and we don't have any callback. Nothing happens. Why? Because neither my character nor my box have the callbacks flags set to say that they should react to callbacks. So one thing we have to do then here is, so if I make my box then have the callback flags for on collision enter, I think that shall be enough to trigger the method to be called. So if I touch bang, we have entity 001 version 1 collided with entity 2 version 1. So it already worked. And if we pay attention, entity 001 is our box, and entity 002 is our character. So the order here means that entity 1 was info.entity, and the second entity, the one I collided with, was entity 2. How is this order defined? Basically, the entity that has the callbacks flag set will receive the callback on its perspective. So, and it would be the entity on the info, and the other one, whatever the flags it has, will be the other. So if we do the opposite, if we make nothing here on the box and we get the character collider and we make this guy receive on collision enter, save the prefab, disable again here, and we press play, we'll get the inverted order. So let me show that. So bang, now we got entity 2. Oh, now, oh no, it's okay, it's still possible to see. So fortunately, my face is not in front. So now the order is inverted. So we see here that entity 2 is entity and entity 1 is the other one. So what will happen if we set this callback flag on both of them? So what happens if we set the callback flags on both of them is the callback is going to be called twice. Once for each one of them in their expected order. So we have to be careful with that. So here it is. We got the callback called twice. So we entered the collision from the perspective of entity 1. We entered the collision from the perspective of entity 2. And that's it. And this semantics would be the same for, so let me remove them from here. I don't want to get this here, so let's keep it here. So this will be the same for all the other types of collisions, and so the flags define which ones each entity receives, and if at least one of the entities have the callback flag set, that callback is going to be triggered from the perspective of that entity as the first one, as info.entity here. Okay, so that's a good primer on callbacks and these basic components. Basic overview on the physics body component. So interesting things about, you can set kinematic components that you move manually. You can basically get it to sleep or not, and what can get them automatically awaken or not, and some configurations about inertia and center of mass, if you want to reset based on the configuration, or if you want to manually set all these things, and some rotation freeze that we have, and there's all these little things here. They're interesting because you can also change them dynamically from runtime. Even on the every frame predict rollback, it's all fine to change dynamically. So and one cool one, like for example, is the gravity scale. So this allows you to change the gravity, how it acts on each body dynamically, basically by setting gravity scale. So this is available in runtime as well. Okay, so I think that's good for physics. Let me take a look if I have. So no questions here on Discord. So just making sure I say this again. If you guys have any questions, please ask. If you guys have a topic you would like to me to talk about, please ask. I probably will have time to do it. So let's get a bit into the topic of performance. So a lot of people start testing quantum and they jump into how much you can squeeze and all that and so on. So especially because people see ECS and they already think about like massive simulations and so on. So remember that quantum is a deterministic gameplay engine. So quantum is not really about making a super huge city with challenging rendering on that. It's not. Quantum is about building very fast-paced, twitchy, physics-based games, but they run deterministically on all devices. So you have a performance envelope of what you can do, which is pretty big depending on the platform we're talking about. But you're still talking about running at least on verified frames only. We're going to talk about the topic of prediction culling, but you're still talking about running the full simulation on each machine, which means the use we do for ECS is to make sure we can very, very quickly roll back and predict again the whole simulation, and this is going to be fast. But in any case, testing performance to understand if you're inside the performance envelope you need is always important. But a lot of people think about performance, and the first thing they do is they plug in the Unity profiler. So that's not how you measure performance, right? First thing, right away. Profiler is for you to analyze where performance bottlenecks are, but it does not help you give you what is the runtime CPU consumption of your actual game. Why is that? Because a profiler is expensive. It actually is very invasive, and it makes your performance worse, especially the deep profiler, but actually even the normal profiler is. So if you want to measure performance, the first thing you should do is you should not use a profiler, is actually use some stats to see how expensive the whole simulation is. And that ends up to this. So we ended up actually creating a document just to talk about this. And we really, really recommend anybody to, first thing, if you're thinking about performance, take a look at how to profile, how to measure performance, because we have an interesting sequence of steps you should do to try to understand the performance envelope of what you're doing. So normally the first thing you should do is first build quantum in release mode. In Quantum 2, that meant in Visual Studio selecting a release build profile instead of the debug one. Quantum is much faster with release builds. In Quantum 3, because it's everything inside Unity, basically you have here a toggle between the DLLs, and by default we start with release, so it's already good, but you can switch to debug, so you can have a more verbose logging and asserts and things for testing, but we have the release one by default here, so we're already on release by default. So first thing is you go for the release version. Then you should do a Unity IEL to CPP build on your target platform. And you should use what we call our graph profiler. So we're even considering adding the graph profiler to the default SDK because it's very, very clean and easy to use. It's a drag and drop asset that if you add it to the scene, it would show these. It would add something like this to your UI, and it's a very, very lightweight shader that basically on every Unity update it collects the stats of the last call to quantum, and it shows you how long it took to simulate the whole quantum step, including verified frames, rollback, resimulations forward, and so on and so forth, and a lot of other stats. So like how many predicted frames you got, how many verified frames you advanced, what was your ping, when was the last time you actually received data from the network, how long did the render take. So we show a lot of little things. So the first thing you should do is release IL2CPP build, test this. This shows you, especially on an online game, it shows you where your performance ballpark is. If this is all under a nice envelope in terms of CPU of simulation time, not consuming more than 25% of your full delta time, meaning that you have a good room for doing your scripts and your rendering on the view side, it should be all good and you should not worry about performance. If it's above that, then you start to actually use a profiler. So if you do have performance problems, then what you're going to do is you're going to add a profiler so you can see the relative performance characteristics and you check what is taking longer than what else, so you start to optimize somewhere. And for that you have two choices. I mean, we hook everything into the Unity profiler, and via code that's also accessible for you to create entries. We're going to demonstrate that soon. But we also have a very lightweight profiler that we call task profiler that does not do memory profiling, does only time profiling, and it's very, very little invasive. And what we like about it is that you can actually go on an IL2CPP build, use our task profiler, and it's going to give a very, very close to the non-profiler version of the application. It's going to have a value very similar to that, so we recommend you to try it because it's lighter weight than the Unity normal one. But of course, if you're measuring relative performance, you're going to get to use the Unity one at some point. But let me open up the quantum task profiler here. Let's press play, run our game, and let's start recording and take a look at what we have here. So it shows us. So the whole simulation took, so this is a very interesting number. So our whole simulation is taking 0.1 millisecond. So it's 1/10 of a millisecond. So 1/10,000th of a second. So we could run this whole thing here at 10,000 frames per second if you think about it, just the simulation. But you can see very, very detailed where the performance is going into. So you see that the physics engine really uses the multiple threads really well. So we're set to use only 2 threads by default here. I could increase this here. I think that's on the runner now. Is that it? I forgot where we are doing. No. I don't know what skin. Oh, an issue with the renderer here. Okay. Not related to quantum in this case. So I thought it's actually in simulation configs too. I am confused with the delta time. So thread count. So I'm gonna use 4 threads here, and let's see again the task profiler. Press play, record, and here we are again. So now it's using 4 threads. It doesn't make much of a difference because we're actually bottlenecked by the overhead. Our movement system is actually what's taking most of the simulation time from all the systems we have. Well, physics also, because physics has a baseline that it needs to perform. But I think we have our navigation. Yeah, navigation and avoidance system running here also in parallel. We don't need to have the navigation system even running at all, but I added it here just for the sake of it's not taking a lot of time. But anyway, so it's our test profile. It's very interesting. You can save data if you subscribe to Circle and you need to analyze something. You can always save a profile session and send it to us. We can always read that and get some details out of it. So it has some interesting things. So we show on quantum frame by frame case, right? So this is the quantum frame number, and we can group it actually. So when you have rollbacks, it actually groups how long it took on the combined stuff, and you see still the frames separately here. This you cannot do with the well, I think the Unity one will only show grouped essentially, but we have this option to stretch them, which only ours have. But anyway, you can also use Unity. It will also show the use of multiple threads and all. So this is for you to analyze. So you're starting to check performance, and you notice that you have some performance to optimize here and there. So how do you actually do this? So the first interesting thing to do is to use some of the default stuff. So I showed here a bit that allowing bodies to go to sleep, using a little bit of minimal linear integration is going to help this work very stably. And I think the physics, so let me take a look at physics, performance, and optimization. There's an entry for this on the manual that gives a lot of tips on how to fine-tune the broad phase for your expected world size and all that. And yeah, talks about sleeping. I think that, yeah, there's a problem here on the screenshot, so the guys are watching, so they will see. So there are a few tips here that are useful, but Quantum can do something very, very clever, which is what we call prediction culling. So you see here, this is about what we are talking about. So this green area here is actually the playable area from the base configuration we have here. So let me take a look at so world size. If we reduce this to 64, yeah, because we have so this is the nav mesh. So if I reduce that, yeah, that was the nav mesh playable size. So if I make, yeah, so the nav mesh is the green one and the blue one is the physics world. So let's make them match. So I'm making their dimension match better what I have as playable here, which doesn't hurt. But what I wanted to get to is not really about playing around with these. These is on the documentation entry. It's more like sometimes you have a bigger game, right? So it is, even if it's a 20-player game, let's say, you have people wandering around different areas. But what matters in this case for me here, for the context of what we're doing here, is that, let's say your character, you are watching, your camera is focused on where your character is. So do we need to actually predict and roll back the whole game world? And the answer is, of course, not. You don't have to keep predicting everything. Prediction is important for physics interaction. So it's interesting that this box here, interesting, this box went to rest because I enabled sleeping, and I'm not manually putting them to, I think it's still sleeping, and I would have to get it to be awakened by doing an overlap here, I guess. So but anyway, the point I wanted to get to is we're only interested in stuff that's very close to us here. And so how can we do that? So there is a very easy way in Quantum to set the prediction area to only be what you're interested in. And you don't that's not on the simulation side. You actually set that from the view side. So let me close everything again here and let me open just my custom camera follow thing. So whatever, because this is our camera and I'm interested in the where the camera is looking at, so that's the position I'm interested in for the camera side of things. So one thing I can do from this here is that because this is a view and this already runs only for my local character, I'm going to run from here. Now that I know where the camera is looking at, I'm going to do, I think I have game here, dot set prediction area. And I'm going to set the position to be current look position dot to FP version 3, and we define a radius. So let's say 20 meters radius using meters. I think, so with this one line of code here, I'm doing it from the camera script. With this one line of code, we're telling Quantum that we don't care to predict any entity that has a transform that's outside of this area. And that's valid for physics, that's valid for navmesh, that's valid even for your own code running, your own code that is running. I think if I show gizmos, yeah, I think maybe here. Yeah, I think we're not showing that gizmo. I thought we had, oh yeah, here it is. So this red gizmo shows where the area of interest for prediction that we're running here. So 20 is even a law here. We don't need that because that's a radius. So perhaps I can put something like 5 instead, or 8. Maybe 8. Let's run again with 8. I don't want the gizmos here on the game itself. I want to see on the scene. So here it is. So everything inside this red area is being predicted. Everything outside of this area, if we have entities outside of it, will not be predicted. And this helps a lot contain and control the performance characteristics of the game. So if you have 1,000 entities and only 20 of them are inside this area, you're actually predicting a game with 20 entities. And you are running the 1,000 entity game in lockstep, basically with confirmed inputs only forward. And essentially that means that your game, more or less, your online game more or less performs just like the single player game. So on these larger games, because we'll be running the full complex simulation only on verified frames with all the entities, it performs exactly like a local game because it's basically a forward-only game. Prediction, and this is interesting when you look at the profiler data. You're going to see that your, especially with the quantum profiler, you'll see that your prediction frames are going to run much faster than your verified frames. And that basically means you're much better protected against ping spikes when you need to predict a bit more, because you have a much more controlled performance consumption on prediction. So it is a built-in thing. And then one question people may ask is like, can I have a different geometry primitive for the area? So the reason we went for a sphere is because it's cheaper to check just the sphere with distance check for the entities when we have to flag the entities for prediction or not, than to run something more complex. But it is certainly possible to do so, and it really depends on the game. So we have a sample. It's still, this sample itself is not ported to Quantum 3 yet, but it's not necessary to be, because what it does can be done in Quantum 3 the same way, what I'm talking about here. So let me show which sample this is. So people who have access to this thing called vehicular combat. So this sample here actually forwards the culling check for the entities as a callback implemented on a Unity script, and this callback basically uses the Unity camera frustum. So essentially whatever is inside the camera frustum is going to be predicted, and whatever is outside of the camera frustum is not going to be predicted. The reason why that works well on this is because this sample does not have a lot of entities, so the frustum check, which is much more expensive than a sphere check, it's not called that many times. But it's more important to have that than to have a complex object simulated on prediction. So it's cheaper to do that. So it does that, and I think it's explained here on the suspension. There's a few interesting aspects of yeah, no, it doesn't show here on the thing, but in the code it has this example, and it can definitely be adapted easily to the Quantum 3 to Quantum 3's. It's the same API for that, so you can use the same approach of a callback. So you can certainly use then a different. So of course you can use a different geometry check. Shape, a different shape for the prediction check. But even before getting there, just mark, just use something as simple as this, which is set prediction area radius from where your local camera is looking at with a decent enough radius. This makes wonders on a game with a lot of entities. You will cut the performance consumption by a lot when running online. It doesn't, by the way, it doesn't change a single thing when running offline, right? So running offline, you are basically moving forward the simulation, and there is no prediction culling to be done. But once you're running online, this is actually making the entities outside of this area not be part of the simulation. And by not being part of the simulation, I wanted to clarify one thing. So, because this is a kind of a complete course, so let me explain things correctly. So if you think about your movement system here, so this is a filter system that is filtering things, and that includes entities. The entity has a transform, and of course those. So maybe this entity is called. So what that called on prediction tick. So what does that mean? So it means that on predicted frames, entities that are outside of the prediction area will not have even this method called. So you are not updating entities on prediction frames outside of the area. So this method is not even called because this is your custom method. So you don't have to do anything on your code just to save performance from prediction culling if you call entities with that, because it would happen automatically for any entity. Even if your filter does not include the transform, it does not have to include the transform. The data, the culling flag is on the entity itself in our internal data. So as long as the entity has a transform, even if your filter does not know about the transform, that entity is not going to be part of your system. But there are ways for you to go around the culling. So you can say that your system does not use culling. This means that this system is going to ignore prediction culling, and it will run on prediction for all of the entities that match the filter no matter what. So you have these controls that you can go around. The same if you're doing a manual filter. So if you're checking into the manual and you are doing, so let me get here, components, I think filters go in here. No, yeah, filters. So if you're manually filtering for certain component types, like this example here, you can set the filter, this filter struct you receive, you can set it to ignore culling. And then when you iterate, like this while here that's iterating over the filtered entities, you can define the behavior you want to do with culled entities or not. Notice that entity culling is only a thing on predicted frames. It never changes the You never have entities filtered on verified frames. On verified frames, all entities are always simulated. So, but this is always the number one thing to enable. If your game could benefit from it, do it right away. So next tip on performance optimization is time slicing based on entity indexes. So let me explain what that is. So we have our movement system. Let's do that on our character system because it's just an example system. So we're updating our stats with a polymorphic method that's doing something on the entity based on whatever is the spec of the entity. It doesn't matter. But the point is that we're updating here all these entities. And I'm thinking here what I should do because I want to demonstrate. I have a cool thing. I have a cool thing I want to demonstrate now because so first thing I'm going to do is I'm going to make this update stats here. I'm going to make this method very, very expensive. So for int e equals 0, e smaller than 10,000, e plus plus. I'm going to do something like filter dot stats dot actually stats pointer power plus equals 1, and then I'm gonna also subtract 1 just to make sure I do something that tricks the compiler into thinking I'm doing something, so you will not optimize out this loop. So this is a very bad loop. I'm gonna get my concrete implementation of the asset type because that's the one I'm using. I want to make sure that this one here does base.updateStats f ref filter. So I want to make sure I call the base method. So it will be the same. So when we run here, we only have one entity so that has this thing, which is our character. But we're going to trick it very soon. So let me see here. Quantum window test profiler. I only have one entity, so this is still not enough. Yeah, it's starting to show here. So we'll make this thing actually start to show, because what we're gonna do is I'm gonna remove this character stats from here. I don't care about that in my character. My character doesn't need that. Yeah, it's a character, it has stats, but my point is I'm gonna do something very, very silly here. I'm gonna create a quantum empty entity, but I'll make it have a transform. This entity does not have a view. We don't need a view for it. The point of having this entity, I don't need a view for it. What I need is I need to have a transform, and I will add character stats to it. Then I'm going to use my whatever, can be the variation spec. But what we're going to do is I'm going to duplicate this. I'm going to duplicate. So we have 8 of them. Let's just start with 8. And yeah, 0, 0, 0. Can I make this guy also? Yeah, it's also 0, 0, 0. So I'm going to call these entities. So I have 8 of them. They're all in here. So if I run this now and look at it, So I think now our character system, yeah, now our character system is taking most of the time. It's like 0.1 millisecond updating those 80,000 entries because we're looping 10,000 times per entity and we have 8 entities with that character. So I'm going to demonstrate 3 different optimization techniques and the impact they have here. So please bear with me. I'm going to make these separate chapters. So this is introduction. We're going to implement 3 optimization techniques here at this system. And we're going to see how they can help. So we're going to check. So to demonstrate prediction culling, I need to run online. So yeah, we'll try to do that. So we'll demonstrate prediction culling. So we'll see the difference. So that's technique number 1. I'll also demonstrate time slicing, which is the next technique. And later, I'll demonstrate multi-threading. Depending on what you're going to do, you're going to use 1, 2, 3, one of these, or maybe you're going to use all of them combined. So it is always useful to do whatever you need if you want to do a lot of stuff. So let's start with, we already showed how to use prediction culling, but to actually see this making a difference, we need to have even more entities and we need to spread them apart a bit more. So we check that our character is not close to all of them. Perhaps we're not close to even any of them. So what we're going to do is I'm going to move these entities to this corner here. So something like -8, 8. I'm going to duplicate that and we're going to make 8, 8. We duplicate that again and we make -8. We duplicate one more time and we make this also -8. So we have a bunch of these entities on each corner and our performance now is going to tank a bit more. It's still not tank, I mean, this is you just fine to do this, but we'll see that our character system is taking a much longer time now. So it's taking about half a millisecond, just that system, because it's updating. It's stupid. It's a very stupid 10,000 times loop doing actually something. So it is not, don't worry, this is not yet something, yeah, we're doing something very stupid, but it's to demonstrate something. So this is how much it is taking here. So let's take a look at, this is going to be bad online because we're going to be running multi-threading. So let's take a look at, let's run this online. We already showed how to do that and we have the menu, we have everything. So let me just make sure my my menu is pointing to the systems that have everything. We have collision. Yeah, I have all our systems in here. So I can press play and let me add the, let me show the task profiler, Quantum's task profiler here. I don't need it to be so big. So actually, I just drag it here. So I think this is all good and I can test it already. So let's see how that goes. So, okay, we have the lighting issue that I didn't talk about. So we have to make this scene that we loaded additively. We have to make it the lighting source so Unity is not going to mess up the baked lighting. So I'm not going to bother with that because that's not related to Quantum. But here it is. So here's our performance stuff when running. We're not predicting a lot, so I guess let me stop this. I want to do something even more silly. So let me get something else to help us. Let's use Clumsy to add a lot of network lag and see how that impacts our performance here. I'm going to clear this. I'm going to quick play. I am recording. We have our base timing here. Now I'm going to make clumsy at something like 50 milliseconds up, 50 milliseconds down. So our it did not work. Oh, I know why. So I think we're using this port. I'm guessing I should use Wireshark to confirm, but I can just try. Yeah, now it worked. So we're running at 120 milliseconds ping now because I added 100 milliseconds ping from clumsy, and we'll clearly see a difference here. So if we look at the whole history, we had a... So it's still pretty fast, but the character system update... So let me group by simulation. Yeah, that's what I wanted to see. So... Because we clearly see here the moment at which I made clumsy, I added clumsy. Oh! Yeah, but that does not have a big impact. You know why? Sorry. We can make this show up much faster. So actually we're seeing it's not impacting much. And the reason why it's not impacting much, we went really, really crazy and we're running, I don't know how many prediction ticks here, but it's still not, let me change the scale here. It's still not going crazy. And the reason why it's not going crazy is because we're actually doing prediction culling here. So let me disable the culling to actually get that to show up. How bad it can get if you don't use it. So I'm going to comment this line here, because if we don't set any prediction culling area, it will actually not use culling. And the performance is going to be worse. So let me bring back the profiler, clear everything, add quick play, group by simulation, because we see the whole time combined now. It's still running interactively just fine, but we're not doing culling anymore. The point is that we're not predicting a lot. So if I kick in with clumsy, yeah, now we're talking. So now we see hello, hello. Is the audio back? What was the last thing you guys heard? Because I don't have a record of that here. I don't want to have to roll. I don't want to have to watch. Yeah, I restarted my microphone here. So can you guys just give me a tip or when it started to when did it go dead? So I can explain back here. So I'll continue from, so I'm actually here running without prediction culling now, and as soon as clumsy kicked in, our simulation time jumped from in some updates, some Unity updates, it jumped from 0.5 milliseconds skyrocket to 4 milliseconds here. So why? So we'll see here why. Because we're predicting a lot of ticks. And look at this. Look at how long does each frame take. Basically the same time. And this here is a verified frame. Yeah, so this is actually running without prediction culling. Thanks, Luke. So this, yeah, so this is with prediction culling turned off. And you see that I think this would be a verified frame here. And these are the prediction frames. See that they take exactly the same time? And the reason why is that we're not culling anything. We're predicting all those 64 entities, doing the silly 10,000 updates on each one of them. So it's 640 times that stupid thing inside a loop. So almost 1 million calls to that per frame. And we're doing in every one of the frames, including verified and including predicted. So let's now add back prediction culling. And we're not going to get to 4 milliseconds at all anymore. We'll have still a little bit of overhead on the frames, doing the movement of the character and a few other things in our area, but it would not go as bad as this. So please mind this discrepancy here of performance, and let's minimize this now with one line of code. Set prediction area. We run the very same thing now. Hope I should save this, but I will save it. So save it here. Editor culling off, because we can then load and compare if we want to. So now that I saved, I'm going to clear it here. Press play. Quick play. Now we're running with culling, and I'm going to add the lag, and I'm going to remove the lag and stop. See here now? See this here? This difference from this to this? It's almost no difference anymore. Yeah, it does get a bit slower. You do get a bit more spikes, but it's nothing compared to the difference that we had on the previous one. So let's take a look at why. So we're still predicting basically the same amount of ticks here. So this is a very good screenshot here. Look at that. So in the previous one, what we had was something like this. So this was the time for the verified frame, and then we would have 6, 7 of the predicted frames taking exactly the same time, and they would just skyrocket in time, right? Now, our prediction ticks are much lighter weight because we have culling enabled, and that means those entities outside of this area are not getting updated until we get close to them. So we can make this go a little bit worse if we get close to those. But remember, I'm doing something just to demonstrate these are very silly things, like updating 10,000 times on each one of those entities. So it is very, very silly. It's just to exaggerate what you get. But you clearly see here the difference. So let me save this as culling on. And I'm going to load the culling off. Bang. See? So let's get one of those. See here? So this is with culling off. And you see how worse it gets when you add clumsy. So now let's load again the culling on with the same scale settings here. So culling on. Bang. Here it is. This is the difference. So even when you predict a lot of stuff, here's what you get. So it's much, 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 much lighter weight. So this is optimization technique number 1, prediction culling. Let's go to number 2. I'm gonna disable culling, so we're gonna focus on just that. No, actually, no. Thinking here. I'm going to disable prediction culling, and then we're going to do the two of them combined, because what I'm going to do here is something interesting. So we're doing something silly. So check, done. Let's go now for time slicing. So because we're doing something silly, so for each of one of those 64 entities, we're doing something very, very, very heavy, which is we're updating 10,000 times something. It's very stupid. But sometimes you do on your game some heavy updates on some entities. So one good example of that is when you're using our bot SDK and you're doing NPC AI, depending on the technique you're using. Normally, the hierarchical finite state machines, they're very, very lightweight. But if you go for behavior trees, they're a little bit heavier. If you go for goal-oriented action planning, that's much heavier. So it really depends on the AI techniques and actually what you do on your nodes. So if you're doing a lot of queries, a lot of complicated stuff on your nodes, AI may get expensive, right? So one cool thing to do is, first thing is that when doing AI updates, one thing you should right away do is that, so prediction culling is normally good for stuff that you still want to be interactive when close. There is stuff that you right away say, I'm gonna update this only. So I forgot that, right? So prediction culling is something that automates the process of deferring stuff to verified frame. But let's say technique number 2 would be to manually defer to verified frame only. So it's something that you don't update at all, so you run certain systems only on verified frames. So that's a common technique as well for AI. Normally AI, one cool thing to do. So common for AI. So common stuff for AI is manually defer to verified only decisions, which is heavy, and which is heavy stuff. And you keep predicting movement steering kind of stuff on AI. So you should plan to do your AI into 2 steps, so you have a more heavier AI machine that does decisions, and this one you can definitely defer to verified frames only. But besides that, you keep predicting the movement, and then you apply prediction culling. Because prediction culling is going to mean that this part here is also only going to run on entities that are very close. But this one here is already only on verified frames. So this is a common technique for AI. I'm not going to cover that here because we're not doing AI. I want to work on these here because there is one extra thing you can do. So these very, very heavy decision things you can do on verified frame only. Sometimes they are so expensive that it makes sense to actually also time slice. By time slicing here, I mean, so if I have 64 entities, what about updating 1/4 of them on each frame, changing which ones we're going to update? So I update, so if it's 64, I'm going to update 16 of them in one frame, the next 16, then the next 16, then the next 16, then go back. So we're going to update them intercalating like that. And how can you do that? There is a very easy trick to make that happen. And that's what we're going to do here. Because we have this update stats here and we have the frame. What I'm going to do is the following. So I'm going to grab, so we have the frame number, and I'm going to call public int update interval, and I'm going to make 4. So it's going to update every 4th frame. But you don't want to do just check if the frame matches every 4th frame, because you don't want to like update none and none and none and then 64 entities, because that doesn't help. You're going to just get unstable CPU. What you want is actually to time slice to update 16 of them on each one of the frames and keep those in groups. And the trick is to use mod the remainder of the division with the frame number and with the entity index and see if they match. So what you do is the following. So you get the interval value equals frame.number remainder with update interval, and you get frame interval. I'll call frame interval, and then you get the entity interval to see which slice or frame slice. I'll call it frame slice value. So it's going to be 0, 1, 2, 3, 0, 1, 2, 3. And what is the entity slice on this one? So it's going to be entity is going to be the entity slice. So what we get is we get filter dot entity dot index with update interval. And what you do is if frame slice is different then entity slice, you return. I'm not going to update. So I'm only going to update entities where this match. And the funny thing is that when you have a frame number that is going to divide by 4 exactly, we're going to get 0 here. So we're going to update only the entities that have indexes 0, 4, 8, every fourth. And then, so this gives a very good balance, especially when you create these entities in batches. It gives a perfect balance in that case. So we're using update interval 4 here. So this basically means that the update rate of this entity is not going to be 60 Hertz, but it's going to be 15 Hertz. But for AI decisions, this is just fine. So this is a good trade-off to do. So let's take a look at how this behaves now. So I'm going to clear the whole thing. I think we have culling disabled. So I don't want to, in this case, I'm thinking here, because we're not changing this. Well, we can change this dynamically. Funny fact. So I'm going to demonstrate this differently. I'm not gonna even run online because we're now isolating this test on these verified frames only. So we're running this local. We have all the 64 entities. They're all running. Here's our time that the frame takes to update. Normal stuff. What I'm going to do now is it's updating. It's actually slicing the update, so it's not taking the full time here. So you see, it was about 0.4. Remember, it was 0.4. Hello? Hello? I think it's working again. Yeah. Okay. So we can modify these values in runtime. So I think this will let us demonstrate this. So if I start recording, so we'll see the time jump here. I'm going to modify this to be 1 and bang, see how long it takes now? We can clearly see the stuff. So if I make this 10, we can make it go very, very fast. So let's change the scale here so we see. So essentially when I was using interval, when I was using interval 4, our system was taking roughly 0.1 millisecond. When I changed to use interval 1, meaning that I'm going to update every entity every frame, we got back to close to 0.4 milliseconds per frame. Then I did a crazy thing and I started updating every 10th. And then we get back to 0.04. Of course, there is a bit of overhead, so it's linear, but with a bit of an overhead. So, but you guys got the point, I guess, right? So you can, and when you combine this with the fact that you're going to be running things probably only heavy things only on verified frames, some things only on predicted, some unpredicted for close ones. If you combine that with time slicing, you can get a pretty good optimization out of this whole thing. So I'm not going to demonstrate this together with the prediction area because it is kind of like two complementary things. Normally you use the you use the time slicing technique for very heavy stuff that you already defer to always happen only on verified frames. So prediction culling is normally for the steering movement part of things. We're just using a heavy thing here on prediction for demonstration purposes. But multithreading, which is the next topic, is an interesting one. So I'm going to disable the time slicing and the prediction culling for us to test the next technique, which is multithreading. And then we're going to... prediction culling... Well, I think for this technique here, we again can ignore the prediction culling because it combines with it as well. But I want to demonstrate it individually. So, but I'm going to focus on the update interval and the next technique because they can be combined really well if done correctly, and they add on top. So as I said, prediction culling normally applies to very twitchy thing updates that you normally don't move to verified updates, whereas time slicing applies to heavy stuff that you move to verified frames. So it's already not something that prediction culling helps at all because it's stuff that you're already doing on verified frames. But the next technique can be combined with time slicing, which is using multithreading. So I did this already for people who watched my stream on FPS. We already demonstrated how to do this, but I'm gonna do it again here. So we have this character system that's doing system main thread filter. I hope I will be able to do it here. I think I will. So what we'll do now is we're gonna make use of multithreading. So there is a hidden documentation entry. So let me give something for people who watch the stream. So I think I have multi-client, I have multi-threading. So people who watch the stream, you can type in this manual multi-threading and you get access to this hidden document. We just don't advertise much about it. It explains you how to do multi-threading stuff in the quantum task system. So quick disclaimer here. So using multi-threading in quantum, you have to know what you're doing because it's unconstrained access to the stuff. You cannot destroy, you cannot add entities, add components in multi-threaded systems. This breaks determinism, and it may even break the game. It may just crash, and I mean not crash, but give an exception and stop running the game, the quantum part. But for updating very heavy stuff, it is very useful. But there are a few rules. It depends on the type of task you run. So you can custom design a complex system that does both data parallelism and task parallelism. If you know what these concepts mean, there is some information for you here to read and see what you can do with that. But I'm going to focus here on a very convenient way of doing data parallelism, which is we're going to update different entities using different threads. We have 64 entities with a very heavy update. What we're going to do is we're going to make them be updated at different threads. So there is a very convenient system called system threaded filter that has the same API as the system main thread filter that we have been using. And it has the same syntax for us. So what we're going to do here is that we're going to use system threaded filter instead of the normal system. And what we're going to do here, we're going to replace the old update with this update because it uses a different variation of the frame type called frame thread safe. And frame thread safe does not have the full API of frame, so there are a few things we have to fix. One of them is the asset. I hope I'm going to be able to actually demonstrate this because I think I've thought, why can't we get assets? No, it is find asset here. Why isn't it accessing this? Oh, it cannot be inferred. Okay. So this one we have to say character spec. I think we have to oh no. Oh yeah. Dot ID. Yes, this works. Okay, so there is a little variation here. So it does not have the code generated part of the asset finder, but you just manually use the ID and you explicitly say what the abstract type is, and it will work. But our update stats was expecting this to be a regular frame base, so let's fix that. We can make that, because we're doing the frame number and all that. So let's make the thread safe. We're not using anything crazy. We're just getting the frame number. That comes from the frame thread safe API. We need to do that on the other types as well. So let's get here the asset type. So character spec, frame thread safe, of course. The concrete types now. So this to be an override has to be frame thread safe. Same for the other type. Oh, the other type does not implement the method, so it's fine. Okay, so we're receiving frame thread safe this time, and that's it. Now our system, so this call here is polymorphic and multi-threaded, meaning this this is not multi-threaded. What is it is being called from a different thread, but this is multi-threaded. So this, if we have 64 entities, what this is going to do is it's going to create slices of the entity filter. So let's say this is a verified frame only, and this is, so we can also skip here prediction. So we don't care about prediction, as I said. So is predicted, if is predicted, we can just return. We are not updating this now. Damn it. So if is predicted, then return. So we don't care on prediction frames. So let's just try to do this. So what this is going to be called is going to be called for for one part of the entities in one thread at the same time for another part of the entities in another thread. So the careful thing here is that when using this technique, each entity should only read and update itself. You cannot update itself and read others. If you're not moving your entity or modifying your collider or of the others, so maybe it's okay to query in parallel and read about the world, as long as you don't read on the same components that you may be modifying, because they may have been modified by different threads. So don't do that. As long as you don't do that, you only modify own entity, and the data you read is not being modified by this system, you are good to go. And you can even control how big the entity slices are for putting in buckets into the threads here. The default for that is 8. Because we have 64 entities, this, I think, do we have 64 or 32? I did not even pay attention. I think we only have 32. Yeah, we only have 4. Yeah, we only have 32 entities. So it's going to actually split 8 of them into each one of the threads. So it's now using multi-threading. And remember, it was with our spec asset is using now interval 1, meaning that each entity is being updated every frame. So the difference in performance now, it's going to be done by the multi-threading. So let's see how that goes. So let me clear all that. So see that we are, actually I thought it was 8, but I'm now thinking it is 16, because you see, we're not using the 0.4 milliseconds, we're using 0.2, about 0.2 in total. But it is only using actually load on 2 threads. I think it's because it's actually slicing, the default slice is 16 and not 8. So we can modify that by code here. On a multi-threaded system, we can say slice size. I can make it 8 or even 4 if you want. It's a very expensive per entity thing. So it will probably use all 4 threads now, and instead of 0.4 milliseconds per, yeah, it is using 4 threads now. And instead of 0.4, guess what? We're back to 0.1 milliseconds. How cool is that? So we're not using time slicing. So we're updating all 32 entities on every verified frame here. But our system is back to using only 0.1 milliseconds, not 0.4 milliseconds. Why? Because we're using all 4 threads. Let's combine the two things together. So we do time slicing and multithreading. And you know what? Look at that now. We're at 0.0. Whoa. Is that? Yeah. That's, yeah. It should be 0.025, but of course we have overhead, and so it's about 0.030 now, not 0.1. So we got a very, very decent speed up here combining the two things. So remember, without multithreading, without the update interval, we were using 0.1, we were using 0.4, 0.5 millisecond for this system alone. Now combining time slicing and multithreading, we're down to 0.03. So this is a 10, more than, it's like 12, it's not full 16, it's 12x speed up, which is amazing, honestly. So combining multithreading, yeah, this is cool, right, Daniel? Because yeah, I didn't plan for this, so this was an emergent idea. So cool. 0.4 to 0.03, combining two optimization techniques. So so done here. So playing around with this, and yeah, 32 slice. So I think adding slice 4, it might add a lot of overhead. But if you have very, very expensive stuff, combining these two techniques, and I would say something more realistic, right? So if you're talking about PC, you can count on having about 4 threads to use. So it's realistic to think about this. Time slicing is always good to use. So time slicing over 4-5 frames is always realistic to think about, especially for AI decision-making stuff. It's okay for the decisions to happen even every second if you want to. So I would not see a problem in making like update interval 10 here if I have a big number of entities. So I just slice them over time. But if you're doing a mobile game, time slicing, always good. But multi-threading, the thread count stuff on your simulation config, it's more realistic to consider that you're going to have actually 2 cores available. There is a way for you to schedule, to use dynamic scheduling. So you define here in Quantum to use up to 4 threads, but on the script that actually schedules the tasks you on different platforms, you can lower that number, let's say to 2 on mobile. And I think that's on the document. So I think we explain, yeah, scheduling barrier. Here it is. So sorry. Scheduling barriers is for task-based parallelism. Change amount of worker threads per platform. So there is an entry on the document I shared here that explains how to do that. And you may ask, why would I use 4 threads on PC if mobile is going to be my bottleneck with 2 threads? The reason is that you may want to run so fast on PC to get a beefier renderer. So perhaps your game runs at simulation rate 30 Hz, and you want to make sure your simulation time on PC is so slow that you can run your rendering at 90 Hz, 120 Hz monitors, and it doesn't get any frame skips. So you want to have room for rendering on PC to run very fast, perhaps on the rendering side of things. So that's one reason. So you always want to use as low CPU time on each platform as much as possible. But of course, you need to make sure your game runs fast enough for every platform. And if we see these techniques here, so prediction culling applies to everything, time slicing applies to everything. Multi-threading is the one that it's not so universally applied, although for 2 threads this is still fine. let me take a look at our plan here. Actually, we're done. So this was everything I wanted to cover on today's stream, but I still have kind of like plenty of time for questions. I hope some of you guys may have a few questions this time. There's a bunch of people watching, so if you guys have any questions, please ask now. Otherwise, I'll just be looking at stats here. I can think about a couple of topics here. Let me take a look at the document. Oh, there is one topic I wanted to talk about. So Luke, Daniel, Juan, do you guys have anything I may have missed that it would be okay to talk about, perhaps? Because I do have a topic I want to get to, but I'm really waiting to see if we get any questions before that. So checking on the other channels here if everything is clean. Okay, since I don't have any questions, I'm going to jump into the next topic, which is, let's open a new, oh, sorry, not here. Let me open a new document here to show. Oh, commands and predicted commands. Good point, Daniel. I'm going to talk about commands before we get to the next topic. The next topic is going to be what should be the next Quantum 3 stream about. I'll talk about this after I demonstrate commands. So skip that here, and let's talk about commands a bit. So good suggestion, Daniel. I didn't talk about commands before. So we've been using regular quantum input, right? So which is you define some constructs on input and you poll inputs on Unity, and then you have the frame input available on systems like we demonstrate here on our movement system. So let me get my movement system. So here's our movement system, and we just grab the copy of the input for this player for this frame. But the input struct is a bit rigid, right? So you define the data that goes into the input here, and it's, yeah, you can add a bunch of buttons. Let's say you add 8 buttons. A good point about buttons is that they take only 1 bit when sent over the wire. You bit back the data. So if you put 8 buttons, they're gonna make a single byte. And so you add a bunch of data. Normally you use input for direct controls, which is, think about if you have you can have a virtual gamepad and you have a bunch of, a couple of directions. If you have a dual thumb, maybe one of them you want to be analog, so you have magnitude as well, and a bunch of buttons, which are a couple of analog buttons perhaps. So you map these things that are direct inputs to be this input struct. But in many games you have things like, oh, I want to do this now, and this is like infrequent kind of commands you want to send. So think about RPCs that you send to a server saying, hey, here's my, I'm by this character here, and I'm looting, and there's a bunch of stuff from it I want to loot from this entity, but not everything, just these 2 things I want to loot. How do you send that as input? So how do you, for example, choose from this particular entity I'm trying to loot this and this and this item from it, from its inventory? So that's where you use commands for. So commands are classes. Let me try to create a command here. So they work just like inputs, but they are reliable. They always get to the server. They will always be adapted to they will always be attached to the input stream, but you can have as many comment types as you want, and you send them only occasionally. They only take space on the input stream if you do use them. And prior to Quantum 3, commands were verified frame only. So you would send, and there will always be a delay until the command would reach your client and all the other clients. Starting with Quantum 3.0, commands are also predicted just like normal inputs. So this means that you don't have any delay when you apply a command. You still have the local prediction of it normally. So it's very convenient to use. So let's demonstrate how to use a command here. I'm going to fake something like we're going to loot something from an entity. We don't have an entity to loot from, but I'll just send some stuff to test. So let's say commands on our simulation stuff. Commands. So let's create a C# script. I'm going to call it loot command. By the way, I requested to have, I showed so this thing about having a snip, a template for system and system filter was something I requested, and Jonas nicely, kindly implemented here. And we have an input script example and a few other things. So the input script is the polar callback thing. So we just added for entity view component, entity views context, all this stuff that I've been demonstrating. We have these little templates that help you create a minimal thing. We shall have one for commands, okay, Jonas? It's the next one. So I just noticed here. I think the other one was, I think I showed him another one today. I forgot what it was. That will be nice to have a template for. So we don't have one for commands, but we will. So let's do manually for now. So no using Unity entity namespace quantum. I'm gonna do. So this is what the template's gonna give us. So we don't have to do it like this. So loot command is gonna inherit deterministic command. Why didn't you accept this? We don't need this. Oh, okay, yeah, forgot about that. So a command has to be binary serialized. So we don't use something like JSON or anything like that. So you do have to manually serialize the data you want to go into a command. So I'm going to demonstrate something here. So let's say we're going to, so our command is going to have entity ref, the entity we're looting, and our command is going to have a public int array or byte array. So let's say, why byte array? It's because we may loot multiple. We may want to loot multiple items from the entity inventory. Let's say the maximum number of items in a single inventory of an entity is 256. So I'm adding a variable byte array here. So indexes to loot, to try to loot. So we have to manually serialize, but it's very convenient for many of the types. So serialize ref entity. We can serialize an entity ref. Stream.serialize array. I think ref indexes to loot works because byte array we know how to serialize as well. You can serialize any type of array if you provide the serializer for the individual type as well. But this is the easy one. So this works both for when we're sending the command, it's going to serialize the data and attach to the bit stream that goes up, but also when the command comes down, it can be deserialized. So okay, here's our loot command thing. So just like other kinds of input, we need a way to send this type of input from Unity when we press a button or do something like that. And you can also do something like you need to consume this somewhere. And I'm gonna demonstrate this consuming it here from the movement system, because we know the player number from the link that each entity has, so we can try to see if this player is sending a command or not. So I will start with this. So because we know the player, so let's evaluate if we have a command. Loot equals frame.get player command filter.link.player as loot command. I think this is how we do it now. Yeah. If loot is different than null, then we're gonna log.info loot received, and plus I'm just gonna log the loot.entity. I'm gonna log the entity, and plus space plus loot dot indexes to loot dot length. I'm just gonna say how many indexes, how many things we added to this byte array to make sure we see it in both ends. And we're gonna see this being logged multiple times, because this is gonna happen on a verified frame and on prediction frames as well. So let's make sure we also add here plus f.is verified, so we know if it's a verified frame or not, because this is going to happen a lot on prediction and then on verified frames if running online. So we can demonstrate that the prediction also happens. So okay, so that's it for the simulation. It shall already run, but we're not sending any commands, so that log is never going to happen. Let me clear. I don't need to recall this. We're not looking at performance anymore. So why doesn't this have... Oh! What is that I'm trying to do here that's breaking? Who has a camera follow that does not have a player link? Oh, of course, this guy. Forgot to disable it. Okay. No errors. Like it that way. So no commands, no errors, but no commands, because we're not sending anything. So let's open a script. I'm going to open a script of my character itself. I'm messing up with my scripts now, but it's not doing clean stuff anymore. Now let's use our animation view stuff just for simplicity here. I'm going to use the regular Unity update here. Public updates. If Unity engine dot input dot get button. I think there is a fire button, if I'm not mistaken. If I get a fire button, I'm gonna call game dot send command. Hey, super cool this, right? We can send a command for your first player, or you can say you can send a command for a specific player if you have multiple players controlled by the same game client. So couch game, multiplayer, you have 2 players on the local game, you can send commands for each one of them individually using the local reference slots. So your first local player 0, second local player 1, always reference to your local client. But we need to create a command, so let's use loot command equals new loot command. You can poll these things if you want to. I'm not going to do any pool these things if you want to. I'm not going to do any pooling. So I'll just say command dot entity equals entity ref myself. I'm faking this. I'm saying I'm looting myself. It's not gonna be the case. It would be more like you query around and whatever is the closest, or if where the person clicked, it's gonna be the entity you're gonna loot using a raycast to the quantum physics engine done from Unity. You can always do that, but we're not doing a full game here. So what I want is do this, and then I want to make sure I also add index to loot equals new by array for 4 bytes, just saying I'm looting 4 items into this, and I'm gonna send my command, my loot command. Let's call it loot. That's it. Let's also debug.log, which is the Unity log sending command. So we'll see that we'll send this once. Oh, it's not get button down. In this case, is get button down. So I want to make sure I only on the first time it's clicked. So first time clicked, we'll get that there. But before even doing that, I'm gonna clear it here. Oh no, there is no fire. Let's take a look at the ones we have. So project settings, input manager, horizontal, vertical, fire 1. That's how it is called. Sorry. It's called fire 1. I think that's going to be the left mouse button. So let's clear everything so we don't. Now click. Oh, I got a. Oh yeah. I know what I made. Where I made a mistake. I'm gonna explain. But we're actually sending the command. But there was an issue when trying to decode the command. It was actually sent and added to the input, but I forgot to tell Quantum that command exists. So different than assets, commands, it's a bit like systems. So systems, you have to tell Quantum which systems to run. Commands, you need to tell Quantum which command types exist, so Quantum knows how to serialize them. And we do this by using the command setup user, and we can add factories.add a new loot command. So now we're telling Quantum that this command type exists. It's a bit verbose in this case, so don't forget to do this. You need to add your command to the factory list, and now it will be able to decode it as well. So the encoding was correct. Let's clear everything here. Bang. So now we send the command and we received it for entity 34, which is actually our entity, and 4 as the size of the byte array. Decoded everything correctly. If we had sent some indexes on the bytes of which items to loot, you would be able to decode that. Of course, you would check if that actually exists. You would not execute a command if it doesn't, if it will crash anything, so you don't do that. But here it is, it's working. But we're not running online, so this is only running on a verified frame because this is a local game. So let's run now online and see how that looks when run online with prediction and rollback. I'll also make use of our friend Clumsy, so it will run with a considerable lag. So we see a lot more prediction. So let's spawn our guy here. Here it is. And so, yeah, one is enough for us to take a look. So this is, I'm bothered with something. I'll get there. So we had 4 predicted ticks with the commands being executed locally because it is a predicted command, and then finally the confirmed one came and it was finally executed. So this is expected. We're predicting a rolling back and resimulating all the time, and our entity is inside the culling area, so it is being sorry, yeah, yeah, our entity is inside the prediction culling area. We're actually not using culling, so well, there was one thing here. No. So this is it for comments. Let me disable clumsy. Let me see if we have an extra question. No. So Daniel, thanks for the suggestion. So this gives a good framework for people who want to try to take a look at commands. So yeah, it was on front. So the last one was the verified frame one. So we have 5 predictions of the same tick multiple times until we get the confirmed inputs, because we're running with a considerable ping, and we eventually got the final version of it. So thanks for the suggestion. So this gives a good framework for people taking a look at what commands are. So last thing, as I said, what should I do on the next stream, right? So let's focus on this here a bit. So here's my thing. So with today's stream, I basically covered most of the most important features of quantum. I did not stress every single possibility, every single thing on each one of these, not even close, and not every single detail, but these are like already 2-3 hour streams, which is more than enough of time. And so we might create a few smaller streams or videos talking about specific topics. So I plan, so I have one that I want to do about, so with Quantum 3 being on Unity, how can you still keep the simulation decoupled? Can you still export the simulation? Yes, as I discussed at the beginning, but how do you do that? Because it's all done inside the Unity scripts now. And we have, so the SDK comes with an assembly definition setup that basically does not reference Unity from the quantum simulation stuff. It does not have any reference to the Unity DLL. So I'm going to talk a bit about like what are the basic rules and patterns you should use to keep your simulation thing very decoupled from Unity, so you're going to be able to always export it. And the simulation exporter actually would show a compilation error if you make one of the mistakes I'm going to talk about. So this is going to be in the future a separate stream. It's a very special topic about exporting simulation to run from outside of Unity. But what I actually want to do on the next stream is I want to develop a game prototype. Because for these 2 streams here, I actually focused on showing what the features are and how you use the features. But I want to now focus on a more, let's say, usual use case, which is you have an idea, you want to prototype something. How do you do that with quantum? How does it turn out? How do you use these features to your advantage to realize your prototype? And because I want to have that, the actual question is, what should be this prototype? And I'm leaving this as a question here, so please feel free to tag me on our public or circle Discord if you have an idea or something you would like to see about what should I prototype. So this is an open question. I have some stuff I like to do, but I'm not set on any particular idea yet. And so I'm open to suggestions, and I will make my considerations, and based on the suggestions I make, come up with a mashup or some combination of a mashup of different ideas and some stuff I think about. But just to give a bit of a framework, it has to be something focused on gameplay. So I mean here, if you wanted me to do something that requires us to do a lot of content, like a lot of different unit types to be able to get something meaningfully interesting, it might not work, right? Of course, it's about, so creating too much content, creating too much graphic intensive content is also not the focus. So not graphic not graphic centric. So it's not about really graphics centric. So it's not about doing something visually crazy. It's about gameplay. And I also ideally something that is I would not like to say common, but it's is straightforward. By straightforward, I mean it is that is challenging to do in multiplayer, but not necessarily challenging to do in single player. It's one idea, but I'm particularly dodging stuff that is that requires you to do very bespoke stuff. So if you're talking about building something like Minecraft, which requires basically me to write a specific physics engine to do voxel-based terrain, which is something that it can it be done? Definitely. Does quantum make sense to it? Absolutely. But it requires basically you to write the physics engine and the voxel engine to work like that. And I don't want to do that because it's too much time into something that's very niche, very specific. So that's what I mean by straightforward. So something that we shall be able to do with a regular physics engine like we have, or something that you can do combining physics, navigation, and a few clever uses. So with that said, that's it. Please drop suggestions over Discord. You can tag me for that. If it's about this topic, please, you can tag me or tag Luke. Yeah, Luke, I'm telling people to tag you, sorry. But yeah, we're welcome to suggestions here. So anybody watching this afterwards, please, there will be some time for this. The next stream is again going to be about Unreal. I have to finish the Unreal game, and we're close to that. So we got good progress last time doing the lab times and other things. So I plan to do another one about doing a basic AI, a racing AI for us to test, and then at the end do an online test, and that's it. And then the next one is going to be this that I'm talking about here. But again, I don't have anything set yet. Please send your suggestions. So since I did not get any new questions or suggestions for topics to discuss here, we're going to stop for now. And thank you so much, everyone who stayed with me here all this time. It's really appreciated the interaction, and hope you guys enjoyed. And see you all next time. And please send suggestions for the next for the game prototype. Everyone have a nice day or evening. Bye.